Welcome! In this video, we'll solve a problem involving a first-order linear differential equation and definite integrals. Let y equals f of x be the solution of the differential equation dy dx plus x y over x squared minus 1 equals x to the sixth plus 4x over the square root of 1 minus x squared for x between -1 and 1, such that f of 0 equals 0. If 6 times the integral from -1/2 to 1/2 of f of x dx equals 2 pi minus alpha, then we need to find the value of alpha squared. First, let's solve the differential equation. It's a first-order linear differential equation in the standard form dy dx plus p of x times y equals q of x. Here, p of x is x over x squared minus 1, and q of x is x to the sixth plus 4x over the square root of 1 minus x squared. We need to find the integrating factor, if, which is e raised to the power of the integral of p of x dx. Let's calculate the integral of p of x. The integral of x over x squared minus 1 dx can be solved using a u substitution. Let u equal x squared minus 1, then du equals 2x dx. The integral becomes 1/2 times the integral of du over u, which is 1/2 times the natural log of the absolute value of u, or 1/2 times the natural log of the absolute value of x squared minus 1. So, the integrating factor is e to the power of 1/2 natural log absolute value x squared minus 1. This simplifies to the square root of the absolute value of x squared minus 1. Since x is between -1 and 1, x squared is less than 1, so x squared minus 1 is negative. Thus, the absolute value of x squared minus 1 is 1 minus x squared. Therefore, the integrating factor is the square root of 1 minus x squared. Now, multiply the entire differential equation by the integrating factor, square root of 1 minus x squared. The left side simplifies to the derivative with respect to x of y times the integrating factor. The right side simplifies because the square root terms cancel out. So we have d dx of y times the square root of 1 minus x squared equals x to the sixth plus 4x. Next, integrate both sides with respect to x. Integrating gives us y times the square root of 1 minus x squared equals x to the 7th over 7 plus 4x squared over 2 plus a constant c. This simplifies to y times the square root of 1 minus x squared equals x to the 7th over 7 plus 2x squared plus c. This is the general solution. Now, we use the initial condition f of 0 equals 0, which means y equals 0 when x equals 0. Plugging these values in, we get 0 times the square root of 1 minus 0 equals 0 plus c, which means c equals 0. So the particular solution is y times the square root of 1 minus x squared equals x to the 7th over 7 plus 2x squared. Solving for y, we find f of x equals x to the 7th over 7 plus 2x squared, all divided by the square root of 1 minus x squared. Step 2. Evaluate the integral. We need to compute I equals 6 times the integral from -1/2 to 1/2 of f of x dx. Substitute the expression we found for f of x into the integral. We can split the integral into two parts. Let's look at the first part, the integrand. Let's call it g of x equals x to the 7th over 7 times the square root of 1 minus x squared is an odd function because g of -x equals -g of x. The integral of an odd function over a symmetric interval, like -1/2 to 1/2, is always 0. Now, look at the second part, the integrand. Let's call it h of x equals 2x squared over the square root of 1 minus x squared is an even function because h of -x equals h of x. For an even function, the integral from -a to a is twice the integral from 0 to a. So, our integral I becomes 6 times 2 times the integral from 0 to 1/2 of 2x squared over the square root of 1 minus x squared dx, which simplifies to 24 times the integral from 0 to 1/2 of x squared over the square root of 1 minus x squared dx. To evaluate this integral, we use the trigonometric substitution x equals sine theta. Then dx equals cosine theta d theta. We also need to change the limits of integration. When x equals 0, sine theta is 0, so theta is 0. When x equals 1/2, sine theta is 1/2, so theta is pi over 6. Substituting into the integral, we get 24 times the integral from 0 to pi over 6 of sine squared theta over cosine theta times cosine theta d theta. The cosine theta terms cancel, leaving 24 times the integral from 0 to pi over 6 of sine squared theta d theta. Use the power reduction formula sine squared theta equals 1 minus cosine 2 theta over 2. The integral becomes 24 times the integral from 0 to pi over 6 of 1/2 times 1 minus cosine 2 theta d theta, which is 12 times the integral of 1 minus cosine 2 theta d theta. Integrating gives 12 times theta minus sine 2 theta over 2, evaluated from 0 to pi over 6. Plugging in the limits, we get 12 times pi over 6 minus sine of pi over 3 divided by 2 minus 0. Since sine of pi over 3 is square root of 3 over 2, this simplifies to 12 times pi over 6 minus square root of 3 over 4. Distributing the 12 gives 2 pi minus 3 square root of 3. Step 3. Find alpha squared. We are given that the integral I equals 2 pi minus alpha. We calculated I to be 2 pi minus 3 square root of 3. Equating these two expressions, we see that 2 pi minus alpha equals 2 pi minus 3 square root of 3. This means alpha must be 3 square root of 3. Finally, we need to find alpha squared. Alpha squared equals 3 square root of 3 squared, which is 9 times 3 equals 27. So, the value of alpha squared is 27. In summary, we first solved the linear differential equation using an integrating factor and the initial condition. Then, we evaluated the definite integral using properties of odd and even functions and trigonometric substitution. Finally, we equated the result to the given expression to find alpha, and then calculated alpha squared.